Okay, so we're on this page. Okay, this is so-called population growth models of living organisms, no matter animals or bacteria. Okay, so there are two different kinds. Okay, the first one is called exponential growth. Okay, we also call this J shape. We also call it J shape curve. We also call this J shape curve. So as you can see, the living organisms will grow to infinity because there is unlimited. Due to unlimited resources. So it is impossible to happen in real life, in nature. Okay? Because in real life, the resource is limited. Understand? 会发生这个，因为它没有限制的资源，真实的情况不可能。All right? So, for example, if we try to culture bacteria in the lab, so it will be something like this. The growth of bacteria will go to infinity. Okay? It will not stop. It will be non-stop. Okay? So, example. Bacteria in ideal lab conditions. Okay, bacteria in ideal suitables, okay, for in the lab conditions. And the second one, we call this logistic growth. Okay, so in opposite, we also call this S-shape. Curve. You can see the growth getting slower and reach a plateau. Okay, and reach a plateau. Because we say that the exponential growth is due to unlimited resources, right? So for logistic growth, the resources is limited. The resources are limited. So it can reach a maximum population the environment can support. The maximum population the environment can support. We call this carrying capacity. So this is the maximum populations. This is the maximum population that environment can support. We call this carrying capacity. Okay, and we see the growth slow down It's the population ratio plateau. Because the resources are limited. Okay? So this is the real world. I would say this is the real world population example, right? So real world populations like this one, it's impossible to go to infinity. Okay, so this is theoretical. Or we try to do cultures, bacteria in the lab, right? So we provide unlimited resources in ideal condition. So everyone okay? If yes, I can move on. So as I can say, the carrying capacity is the maximum populations that environment can support, right? So there should be some factors. There should be some factors to restrict the growth of the populations. So the factors limits population growth will be two kinds. Okay, the first kind is called density dependence. The density dependent, which means it depends on the population size. So it depends on size. The size matters. Okay, if we have like 100 students in this class, okay, you will feel like enormous, crowded, uncomfortable, right? So that's the density dependent. So the size matters. Okay, which means it depends on the population size. The density here is the density of populations. So it depends on the population size. The density here is mean population size. Okay, so what kinds of interactions? What kinds of interactions what kind of interaction belong to density dependence, including like reductions? So weird, right? Reductions. Okay, someone trying to harm someone, some animal trying to harm someone. Reductions. Disease as well. Okay, disease as well. Competition. Competitions. And also like habitats. TCP, right? Territories. Territory also matters. Even the waste accumulations. Okay, relates to the population too large. The waste. Okay, the waste. Organic waste from, for example, like feces, like urines, 粪便这些. Okay, well, also matters. If it accumulates food, right? And also some physiological factors. Another kind is called density independence. So it doesn't matter about, for the density dependence, the population size doesn't matter. Okay, it doesn't matter about the size. Understand? So it's the population size is not going to be considered. So what belongs to the density independent factors, including like natural disaster, not disease, disaster like typhoons, like floods, like tornado, like hurricanes. Okay, natural disaster, like wildfire, like floods, like droughts, like weather. Understand? So those natural disasters, okay, belong to the density independent, which means population doesn't matter. No matter you have lots of people or very few people, the natural disasters occurs, right? Everyone okay? Okay, next. Okay, this is what I'm talking about, right? The exponential population growth is under ideal conditions. And the population grows very rapidly to the infinity, right? So let's see this formula. Okay, this is very important formula for the exponential. So this is for exponential growth. Okay, not for logistic. So dn dt equals Rn. So n stands for the population size. Okay, n is the population size. R is the growth rate. So the mathematical meanings of dn dt, it's a population over time, right? The t years. Okay. The small letter t here is time. So the mathematical meanings of dn dt is a change in population over time. Write this one down. So from the formulas, from the equation, we can see the growth rate is proportional to the population size, right? So the rule of thumbs, the bigger the population, the faster the growth. If the resource is unlimited, okay? So you need to have assumptions here. You gotta have there is unlimited resources here. Okay, the sources are unlimited. Okay, let's see these questions. Okay, formula is given. A certain population of mice is growing, and also the assignment. Assignment 1 is about starting from chapter 0 until here. Okay. So a certain population of mice is growing exponential. So this kind of lab animals, we provide unlimited resources, so they can grow exponentially. The growth rates are 1.3, and the current population N is 2,500 individuals. So the question is, how many mice are added to the population each year? So this is super easy, just use formula. I give you 1 minute for this. assignment ones will cover from the first class until this class. Okay? Yeah, hands up. Okay. No answer. Okay, let me do it. So, dn dt Rn, right? So, it's just 1.3 times 2,500. 1.3 times 2,500. 3,250. Okay? And also, I already mentioned the mathematical meaning of dn dt is a change. Is a change in population. So you don't need to minus. Okay, you don't need to minus 250, 200, 200 and 500, 2,500. Okay? You don't need to do this. You don't need to do this because the dn dt already the change. Okay? The change in population over time. So 3,250 months are added per year. Okay? Okay, next one. But we say, put a star here. But the problem is, unlimited resources are rare. Okay? In the real world, the resource is limited. Okay, so we're gonna see this model called logistic model. Logistic model incorporates something called carrying capacity. Carrying capacity, capital K. Okay, so carrying capacity is the maximum stable populations which can be sustained, can be supported by environment. So we call this logistic model. Okay? Okay, let's see this formula. So, say dn dt equal change in population. So R equal growth rate of population. So N is the population size. The difference from this one to previous one is we need to incorporate K, the carrying capacity in this formula. Okay? So it's dn dt equals Rn times K minus N. K minus N over N. So therefore, when N is pretty much close to K, the growth will be very slow. Right? And you're gonna reach the plateau. Or just fluctuate years. Just keep fluctuate years. Okay, keep fluctuate, just like process control, what you're going to learn, right? However, and also when N equals K, the growth stops. When n equals k, when the population size equals the carrying capacity, the growth becomes zero. For example, like we have like maybe like 40 seats here, right? If the population, if the student equals 40, then we cannot accept any new students. We no longer accept any new students. Understand? Okay, so this is the very famous so-called the batch microbiome. Microbiome is, I'm sorry. So this is very famous batch microbiome growth. Okay, for example, for bacteria. Okay, so this is the observed behaviors. Starting with the lake. So bacterial cells, okay, starting from here, keep grows. Okay, but there is no significant growth. There is no significant growth. The lake means there is no significant growth. The reason is, at this stage, the bacterial cells, okay, the bacterial cell try to adapt to environment. Because at this stage, the so-called late stage, the bacterial cell try to adapt to environment. 开始适应环境。Understand? So there is no significant growth. And as we have just learned, exponential growth. So the growth rate is rapid. Rapid growth, and it's going to reach maximum. Okay, it's going to reach maximum. Okay, when it reaches maximum, the third stage is called stationary. Okay, so this is very stable, stationary. At stationary, the growth rate is pretty much close to death rate. Okay, so the population stabilized. So this is the stable, it's very stable stage. 很稳定 Alright? Okay. So if the environment goes worse, okay, or get something wrong, the conditions get something wrong, it will lead to the death phase, the death stage. So in the death stage, okay, the cells, okay, few cells as example, okay, bacterial cells die. The cells die faster than they grow. So the population declines. Okay? All right. right, so this is just a comparisons. Okay, so this is the exponential growth model for animals and bacteria. Okay, but actually they are very similar, right? Okay, so this is exponential growth for higher organisms. Okay, for higher organisms and microorganisms like bacteria. Okay, so I think we can start to do discussions. Okay. The microbiome systems. Okay, the microbiome system is microorganisms like bacteria, okay, or like cells. Okay, the microbiome systems with M's, substrates, and nutrients, right, has an initial cell concentration at max of 500 milligrams per liter. The specific growth rate is 0.5 per hour. Okay, 0.5 per hour. So the question asks you to find concentrations at the 6 hour. 6个小时后浓度变怎样? Okay, the first question asks you to find the concentration at the 6 hour. Alright? And the second question is, how if we double time? Okay, how if the condition double? Okay, the condition for doubling, what can happen? Okay, so for this question, I give you 10 minutes to do this. You might check the formulas. Okay, you can check them in the previous slides and see if you know how to do this. Those are questions on textbook. Okay, those are questions on textbook. Okay, that's good. Okay, this one I got solutions. Okay. So, as I can say, student, take a look here. This is for higher organisms, like animals. Okay, like humans. Humans are animals. And this is for microorganisms, like bacteria, like cells. Okay. So, but to be honest with you, actually they are the same. Okay, they are the same. So we're gonna use, because this is for microbiomes, for microorganisms, right? So we're gonna use this formula. So x equals x now, E, okay, mu E. So this is everything we have. So 500 times 0.5 times 6. So this is the answer. So this is the microorganisms. This is bacteria at the 6R, which means it increased 20 folds. Let's see. 20倍了 Okay, the folds. Folds means 倍 20 folds. Okay, you might also say 20 times. 20 times. How many students? 20 times 不是20个时间，20倍。Okay, you might use times or folds. They are the same. 这边的 time 可以加 s， 因为它是倍的意思。Okay, how about we double times? Okay, I give you 30 minutes. Not 30 minutes. 30 seconds if you don't know how to do first question. Okay, 30 seconds. Okay, how to do the second questions? 30 seconds. Thirty seconds for second question. 要做啊，不要只是看啊，要做啊，好不好？ It's very important practice in class. Then when you go back, you just need to do a very quick review, right? And you can spend time on another subject. 课堂上认真听，有练习，回家赶快看一下就好。Okay, second questions. So so the questions say that we're gonna double times. Okay, we're gonna double times. So x over x naught becomes 2, right? So we're gonna use this formula. Okay, natural log x over x naught equals mu t, mean time. So the times, okay, the time equals 1.4 hour. Okay, so after 1.4 hours, the population will double. Okay? After 1.4 hours, the population will double. So let me give you a quick fact here. For microorganisms, it might take 1 to 2 hours to double the population. However, for human beings, if you want to double the population, it might take 40 years. It might take 40 years. Understand? So this is a quick fact. Okay. So this slide tell you the carrying capacity K. Okay, carrying capacity very defined, right? It's maximum populations that environment can support, right? And actually, it's due to the carrying capacity is due to the carrying capacity is due to number one, the limited food, right? Limited food. Okay. Okay, everyone, good news. By the end of this class, okay, not this class, by the end of this course, okay, we're gonna have a pizza party. Okay, so if I just buy one pizza, okay, then you guys might fight for a pizza, right? Compete for pizza. So that's the carrying capacity. Okay, the limited food. And the space, and oxygen. Of course, we just learned some anaerobic organisms, they do not need oxygen. Okay, but most of living things are aerobics. Okay, so oxygen might be the one. Okay, and like addictions and also disease. And many more. So those things will live in our populations. Those factors. Right? So, as we just defined, okay, this is for microorganisms. So X might be the concentrations or populations. So from this formula, you can see, so from when X is close to K, when X is close to K, the growth is close to 0, right? When X is close to K, all the populations, the concentration of microorganisms, okay, the population for high order organism. So X might be concentrations for microorganisms, population for high order animals. Okay, so as X close to, as the concentration of population close to carrying capacity, the growth, okay, the growth approach 0. So there is no growth, right? So this is the formula. Okay, so this is the formulas. These formulas give you the populations. Give you the concentrations of populations. Populational concentration is any time. So the T years, the small letter T years is time. Okay. Okay, next slide tell us the substrate limited growth. Okay, who took biochemistry before? Okay, no one. Okay, this is very similar to enzyme kinetics. Okay, this is very similar to and 9 kinetics. Let's see. And 9 kinetics. And 9. Kinetics. This is very similar to exact kinetics. Okay, so we're gonna skip this. Okay, we're gonna skip this. All right, we're gonna skip this. Okay, okay. I will not test that. I will not test that. Too complicated. Okay. Okay, so let's take a short break. So now it is 2:10, right? Let's take a 10-minute short break until like 2:20. Okay, let's take a short break.